In the last level of Chapter 11, we are going to talk about colligative properties, specifically boiling point, freezing point, and osmotic pressure. These are not necessarily covered on the AP exam, but you're supposed to know the prior knowledge to it. So we're just going to quickly go over it. Because the changes of state depend on vapor pressure, the presence of a solute also affects the freezing point and boiling point of a solvent. Freezing point depression, boiling point elevation, and osmotic pressure are our colligative properties. These are grouped together because they depend only on the number and not the identity of the solute particles in an ideal solution. Boiling point elevation is first. The normal boiling point of liquid occurs at the temperature when the vapor pressure is equal to 1 atmosphere. As seen earlier, we have to remember that a non-volatile solute lowers the vapor pressure of the solvent. So as a result, a solution must be heated to a higher temperature than the boiling point of the pure solvent in order to reach that vapor pressure of 1 atmosphere so that the liquid can change into a gas. A non-volatile solute elevates the boiling point of the solvent. That's the most important thing you need to know here. The non-volatile solute elevates the boiling point of the solvent. So it raises the temperature at which it boils, or at which point it changes from a liquid to a gas. This is called a phase diagram. Again, prior knowledge is needed, but won't necessarily be tested on. We talked about this in Chem 1. The triple point on a phase diagram is the point at which it can exist as a solid, a liquid, and a gas, all three phases at the same time. On the x-axis is the temperature in degrees Celsius and pressure in atmospheres up the y-axis. So the blue line represents the solution, so something added to water. And the red is showing us the vapor pressure of the pure water. Alright. So note that the boiling point of the solution is higher than that of the pure water. Conversely, the freezing point is lower than that of the pure water. So the TF, delta TF, is the freezing point change in elevation, and the depression, I should say, and then the boiling point is the elevation. So notice how our colligative properties of freezing point and boiling point are extending and making bigger the graph, okay? Where the red is what it is normally, so it lowers the freezing point and it raises the temperature at which it boils. So the main thing you need to know about colligative properties is that it extends the range at which it's a liquid. The change in boiling point can be represented by this equation, where the delta T is the boiling point elevation or change in the boiling point temperature. The Kb is a constant that's characteristic of the solvent that's called the molal boiling point elevation constant, and M solute is the molality of the solute in the solution, which we don't need to know this, but molality is the moles of the solute over kilograms of the solvent. So there are a bunch of constants for this if we were to solve that, but we are not going to because we're going to skip example 7 because you won't be tested on it on the AP exam, so we don't need to do the math right now. Freezing point depression happens when you lower the freezing point to be lower than that of the pure solvent. So when you have a solution and the freezing point is lowered. This is a result because the water in the solution has a lower vapor pressure than that of pure ice. And so no ice will form under the normal conditions. The vapor pressure of the ice will decrease more rapidly than that of the liquid water as the temperature decreases. So it's making it freeze at a lower temperature. This means that eventually the vapor pressure of the ice and the liquid water will become equal. And the temperature at which this occurs is the new freezing point and is below the normal 0 degrees Celsius for water. We say that the freezing point has been depressed. This is why we can put salt on the roads and on sidewalks in the wintertime, because the salt will dissolve in the ice and snow in the water, right? And so then it's actually making a solution, and when it makes a solution, it changes the vapor pressure, which then makes it freeze at a lower temperature. So we can melt the ice because it's not at that lower temperature yet. The important takeaway, like I said earlier, is adding a solute to a pure solvent has the effect of extending the liquid range of the solvent, as we saw in the phase diagram earlier. Freezing point depression has another equation very similar to boiling point elevation, but we are not going to be solving for it, so we don't need to worry about that right now. The last colligative property is called osmotic pressure, and this is the excess pressure on a solution compared to a pure solvent when they are separated by a semi-permeable membrane. So solutions that have identical osmotic pressures are said to be isotonic solutions. And this picture is on page 531 in your textbook, but it's showing a tube with a bulb in the end that's covered by a semi-permeable membrane, as you can see in the top picture. And then the solution is inside the tube, and it's bathed in a pure solvent, or bathed in a pure solvent. So the solvent is on the outside, and the solution's on the inside. And so it's showing that there's a net movement of the solvent into the flask through the membrane, so it increases the level of solution by also diluting it inside the flask. And then whenever it reaches a hydrostatic pressure equalizer, or the hydrostatic pressure is equalized, then the solvent flow is in both directions. Because once it gets to a certain point, then it's going to have to start letting some out. And that's when we reach our osmotic pressure. The last thing that we can talk about for solutions are colloids. The scattering of light particles is called the Tyndall effect, and is also used to distinguish between a suspension and a true solution. The suspension of tiny particles in a medium is called a colloidal dispersion, or a colloid. So in the picture, colloids are usually when you can not see through, or you can see the laser shining through. So colloids are classified according to the states of the dispersed phase in the dispersing medium. So there are many different types of colloids, which are listed on page 538 in your textbook. But in a colloid, the particles remain suspended rather than forming larger chunks and precipitating out into solids. So we think that it has to do with electrostatic repulsion, which has to do with the electrons and protons around in each particle. But so on the left is the solution, because you can see straight through it, and on the right is the colloid, because you can see the particles and you can see the laser. So please refer to your checklist to know which problems to do for this problem set.